So here we're going to talk about humidity, where humidity is the amount of water vapor that's in the air. Saturated air that is completely filled with water is at its capacity, or saturation, or at its dew point. Those are all synonymous. Capacity is temperature dependent. Warm air holds more water vapor, and cold air holds less vapor. And we can see that when we look at Table 8-2. Warm air holds a lot more water vapor than cold air. Water adds pressure to the air. When we look at humidity in terms of the measuring value, we can talk about a mixing ratio. This is the mass of water vapor compared to the remaining mass of the dry air, and this is measured in grams per kilogram. But relative humidity is the ratio of the air's actual vapor content compared to the amount of the vapor required for saturation. So when we measure humidity, as we have done several times in class, both in the classroom and outdoors, we express it as a percent. It's a percent of the vapor content, water vapor content divided by its capacity. So we need to know its temperature. So saturated air, the content equals capacity. It would have 100% relative humidity. But we can change the relative humidity two ways. We can add moisture to the air. Adding moisture raises the relative humidity, or removing moisture lowers the relative humidity. So when we talk about measuring humidity, we can change it in two other ways, by adding or subtracting the water, or we can change the temperature. If we lower the temperature, it raises the relative humidity. So we can look at that a couple different ways quantitatively. So the practice problems we did in class, if we know that the water vapor content is 10 grams per kilogram at 20 degrees C, we can use 8-2 to determine what needs to take place to both the amount of temperature. Do we need to increase or decrease to cause saturation? Or do we need to add or condense out water vapor? So when I go back to 8-2, we can use these values here to calculate what the changes need to be. So these problems just further supplement what you should have been able to do on page 10 in the binder. At 10 grams per kilogram, at 20 degrees, we would have to cool that air temperature down to reach capacity. We'd have to cool it 5 degrees, or based on this content, at this temperature, we would need to add 4 grams. In other words, at 20 degrees C, 14 grams per kilogram reaches saturation. Or we could say that 10 grams per kilogram is the maximum at 15 degrees C. And these are just further practice problems you can go through. So relative humidity is temperature dependent. When I look at these pictures here, if I have 5 grams of water vapor and I have, let's say, a relative humidity of 0.25. Notice at 25 degrees C, 5 grams is 1/4 of its capacity. But notice if I double this value here, I double the relative humidity to 50%. So I have 10 grams here at 25 degrees. That's half of the capacity at 25 degrees C, which is 20 grams. And here I have that very example. 20 grams at 25 degrees C is 100% capacity, which tells me the relative humidity is 100%. In this picture, I have 7 grams of water vapor at 20 degrees C. Here I'm going to be changing the temperature. So at 20 degrees C, it has a capacity of 14 grams. So therefore my relative humidity is 50%. If I cool it 10 degrees, 7 grams is the capacity at 10 degrees C. So it's a 100% relative humidity. And if I cool it even further, 10 degrees, it can only contain, 0 degrees C, can hold 3.5 grams of water vapor, and this would be at a relative humidity of 100%. So my dew point. So the dew point is the temperature at which a parcel of air needs to be cooled to reach saturation. Cooling the air below the dew point causes condensation. This could be dew, it could be fog, it could be cloud formation. Water vapor requires a surface to condense on, and we'll call these condensation nuclei. I will type that in. Condensation nuclei. And these are typically dust particles, any type of aerosol. So dew point is a significant topic here, and we'll look at it further here in just a moment. When I look at my daily variations of temperature and relative humidity, observe how temperature increases and relative humidity decreases. This is a result of what is occurring within a parcel of air as temperature changes. So during the warmest parts of the day, we actually have the lowest relative humidities, and where it's the coolest in the day, the relative humidity is the highest. So we're looking at this temperature dependency. We're assuming here that the water vapor content is staying constant. So we're going to look here at what happens to pressure as altitude increases. We'll talk about temperature as altitude increases, and we're going to be talking the difference between the ELR and the ALR. We'll talk about environmental lapse rate and the adiabatic lapse rate. So here we go. Here I have a pressure and temperature chart. Here I have the troposphere, right, the layer in which we reside and life resides here. As I rise up in elevation, temperatures get cooler. It decreases. I also have less pressure. If I look at my x-axis here, pressure decreases. In other words, if I'm standing on this mountain, I have fewer air molecules both on top of me and squishing me from side to side. Air pressure is acting in all directions. So both temperature and pressure are decreasing as I rise up in elevation or in altitude. This is where adiabatic heating and cooling come into play. Adiabatic heating and cooling are changes that occur when air is compressed, it heats up. The motion of the molecules increases. Where descending air is compressed due to increasing air pressure. In air that is expanding, or it would be cooling, this implies air is rising. Rising air will expand due to decreasing air pressure. So when I look here, air that's rising is going to be expanding. It's going to have less pressure on it. So it's going to cool at an adiabatic rate. If I look at that backwards, if air is compressing, meaning moving downward, it's going to have more air on top of it and more air squishing it from side to side. So it's going to compress. As a result of that, it's also going to heat up. So this picture right here is really the tell-all. At sea level, or at this surface here, I've got a parcel of air that's at 32 degrees C. As it's rising, it's going to be expanding. As it expands, the molecules are going to move slower, which means it's going to cool. Really, temperature is the average measure of the kinetic motion of the molecules themselves. So heat is what we determine as its temperature. So as it continues to rise, it's going to rise until it reaches its dew point, or its capacity or saturation. Those are all synonymous. We call this the condensation level. It's typically referred to as the cloud line. Here it's going to rise and cool at the dry adiabatic lapse rate, which is 10 degrees C per 1,000 meters. But at the point at which it reaches this cloud line, it's still going to cool as it rises, but it's going to cool at the wet adiabatic lapse rate. In other words, it's going to cool at 5 degrees C per 1,000 meters. In other words, once you have moisture in here, it's going to continue cooling, but it's not going to cool at the same rate as before it's dry, or before its capacity or saturation, or before its dew point. It's going to cool slower, and that slower is 5 degrees C per 1,000 meters. So here we can talk about air stability, because stable air versus unstable air is really what drives weather conditions. So how stable is the air? Well, stable implies that the air is resisting vertical movement. Warm air is rising and will continue to do so. As it does so, it's going to cool until it reaches an elevation that the air becomes equal to its surroundings. This type of air is considered unstable. Where you find air rising, you consider that unstable. Stability implies that a parcel of air has a tendency to stay in its original position, meaning it's not rising. Unstable air can rise, and weather phenomena occur based on the conditions of the air parcel interacting with the surrounding air. So we got some terms associated. Absolute stability is when the ELR, environmental lapse rate, is less than the WALR, or the wet adiabatic lapse rate. Absolute instability prevails when the environmental lapse rate is greater than the dry adiabatic lapse rate. So environmental lapse rate is 5 degrees C per 1,000 meters, where your adiabatic lapse rate, if it's a dry parcel of air, it's 10 degrees C per 1,000 meters. This would imply it has not reached its saturation. Wet adiabatic lapse rate is 5 degrees C per 1,000 meters. This implies that it is at its dew point already, or at its capacity, at its saturation. If it's stable, ALR exceeds ELR. If it is unstable, the environmental lapse rate cooling exceeds adiabatic lapse rate cooling. So when I look at this, the dry adiabatic lapse rate implies that it's unsaturated air, that the air is rising and expanding and is cooling at 1 degree C per 100 meters, which is the 10 degrees C per 1,000 meters. Descending air is going to compress and warm at the same rate. Here we have the wet adiabatic rate. This is going to commence at the condensation level, or cloud line, where air has reached the dew point. Condensation is occurring and latent heat is being liberated. This changes the adiabatic rate. Heat is released by the condensing water, reduces the rate of cooling. 0.5 degrees C per 100 meters, which is the same as 5 degrees C per 1,000 meters. And the rate can vary a little bit, but we're going to stick with this value right here. So now we have 4 different ways in which air can rise. The first process is orographic lifting, and this is where we'll do most of our calculations from. This just implies some physical terrain has changed a little bit. There's a barrier that forces air to rise. And the results then, in this case, will lead to a rain shadow desert. The second process is called frontal wedging. Now here I have a warm front colliding with the cold front. It just says that the warm front is traveling faster than the cold air, so it's going to collide with it. As it collides with it, the warm air is forced upward. This barrier here is the warm front that's shown here. This is what's got the moisture and the heat, so it's going to rise. Fronts are part of storm systems called middle latitude cyclones, and we'll learn more about these in our upcoming chapters. And these move in a counterclockwise manner. A third scenario that lifts air is convergence. This is when air collides with one another. When the airflow moves into one another, lifting results. When air flows in from more than one direction, it has to go somewhere, but it cannot go downward, right? It's not going to go into the land. So it's going to have to rise, and this is a form of uplift. You have converging winds. If they converge, just like a convergent boundary, they collide, and air only has one place to go. And the fourth and final way, where we get a lot of summer storms develop from, are just general convection, convective lifting. Localized convective lifting occurs where unequal surface heat cause pockets of air to rise because of their buoyancy. So direct sunlight heats up the land heats up the air above it, it's going to begin to rise, and adiabatics takes place. It cools at its condensation line, creating this cloud level, and we can then begin calculating what's happening. In the end, in every scenario where we're talking orographic lifting, frontal wedging, convergence, or localized convective lifting or convection, in all 4 scenarios, we can calculate the rate of rise and the temperature change based on the dry adiabatic lapse rate until it reaches the condensation line. Then it's going to be the wet adiabatic lapse rate once it rises above it. And everything is mathematical.